Welcome back to Arts Learning. In this video, we'll be going over connected systems, which include pulleys and Atwood machines, and how to calculate energy using these. Now keep in mind, the version I'm going to go over is a tad bit more simple than regular Atwood machines. It assumes a few things, okay? It has a few more favorable scenarios, but I'll go over the harder versions when I go over my PDF review, okay? I'll have some of those problems out. So we can obviously go through the hardest ones because that's what this course aims you to do. Tackle any problem no matter how hard. Okay, so let's look at this here. Two masses are joined over a frictionless pulley. So this pulley doesn't have any friction, which is the same thing we assumed when we went over in the force unit, right? We went over in the force unit, same Atwood machines. They either went down or they went up, depending on which one was greater. Then we used to calculate the acceleration. What did we say? The acceleration was the same for both of them. Okay? So if they start from rest, they both have the same speed, right? If one has an initial speed and one has a different initial speed, which is probably, it's not possible in the case of an Atwood machine, so they're both going to have the same speed. Usually you can't assume that, right? You can't assume that just because something has a same acceleration, it's the same speed. But in this case, for the Atwood machine, because they're connected, both of them have to have the same speed. Okay? So you assume that the initial position of this Atwood machine look like this. Okay? So M1 is here. Okay? M2 is here. And then this is the final position. How would you write energy equation for this one? Well, we have an initial energy here of what? Potential energy, right? This is height. So M1GH is a potential energy. And we don't have any other energy here, so that's it. Once you release it as a system, it goes down, right? What does it have when it goes down? Kinetic energy here. Okay, so it's going to have 1/2 mi v squared. Oops, 2 went in the wrong place. What was I thinking of? Okay. And then what's going to happen? This same h is going to be translated here, right? However much this rope falls down is however much this will be translated upward. So this is going to be plus 1/2 m2 v squared. But also remember that once it translates upward, it has the same velocity, right? But it's also going to have what? It's also going to have a gravitational energy because, see over here, M2 now has gravity. So it will end up with some gravitational potential energy. So if I erase this here, yeah. This should give me M2GH, right? So since we know both these velocities are the same, we can just factor this out and we can say 1/2 v squared times m1 plus m2. Because they're the same term, right? And then plus m2gh. Now this only works for this scenario, right? Only the scenario where the m1, the heavier mass, is up here and the lower mass is already in the ground. If not, you can assume how both the masses could, in a scenario, be in the air, right? Then we'd have to add M2GH as well over here. But I'll go over those when I go over my more complicated section of the PDF, right? But right now, let's just look at a more simpler problem. Okay, so we have a 3 kg Atwood machine. M1 is 3 kg, heavier mass. M2 is 2 kgs, lighter mass. From rest, it falls 1.2 meters. M1 falls 1.2 meters. Okay? So, if M1 falls 1.2 meters, which is this distance, then what's going to happen to M2? It's going to translate upward 1.2 meters, right? Because they're both connected in the same rope. If this rope goes all the way down to that means it moves 1.2 meters, right? So this rope has to take it upwards 1.2 meters as well. So if I was to write the equation for this, initially, we have only gravitational potential energy here, mgh. In this case, it's m1, the heavier mass. And then after that, we have m2gh, right? Because it stays at the same height, 1.2, 1.2. That's why these heights are just represented as one variable, right? It gets up all the way over here. Makes sense. The 1.2 has to be translated somewhere, right? Because if this falls 1.2, the rope has a change 1.2, which gets reflected over here. And then plus 1/2 m1 plus m2 v squared, because they both share the same v squared, right? I showed you why that's true in the previous slide. So can we change anything here? We're looking for the acceleration. Oops. Did the same mistake here. Put the 2 as a subscript. I'm wondering where that's coming from. Yep, v squared. So we need v squared, right? So what's that going to be? That's just m1gh minus m2gh. It's subtracted from both sides, times 2 divided by m1 plus m2. Okay? So, in other words, let's pull out a calculator and do it. 2 times m1 is 3 times gh, which is 9.8 times height of 1.2. That's subtracting 2 kgs times 9.8 times 1.2. Okay? Which is 23.52. Yeah? And then that divided by m1 plus m2, right? Which is just 5. Okay. But there's one last step. This whole thing is equal to v squared, right? So I have to take the square root of this. So I'm going to get square root of 4.704, which is just 2.17 per second, approximately. It's actually 2.168, but I can round it up to 2.17. Okay? So that's how you do an Atwood machine using energy principles. So in the next video, we'll be going over a PDF that goes through all these kind of problems and how to solve them, right? The hardest versions of these, because that's what I aim to expose you to. These videos are more of the concepts. It does explore harder questions, like I did a few videos ago, right? With the frictionless and ramps and all that. But that's just to incorporate you with the concepts. The PDFs are the actual hard milestones you need to complete. Okay? And be sure to give me a like and subscribe if I helped you, so I can help more people and continue helping you as well.